Hello, I want to talk about matrix inversion formula today. This will be a very short video. Basically, I already have written the formula here. That's the matrix inversion formula. If you look, you check out Wikipedia, most likely you see a formula like this. I have a matrix A. It's either minus or plus. It doesn't matter. If I use minus here. Minus u times c times v. I'm taking the inverse of that will be equal to this mass here. So it looks pretty ugly here. However, it's pretty useful. Typically, one of the very much important use of the matrix inversion formula is basically when we have a pretty large matrix A, and we just want to add a low rank matrix to that A matrix, and we want to compute the inverse again. So for example, like in the pretty much extreme case, if this additional matrix here is actually just a rank 1, so therefore this may actually can be decomposed as just u multiplied by c times v, where this c here is actually just a scalar. Then in that case, if you look at that, we already know the inversion of A. We know the inverse of A. So these are all known. And so we just need to compute this guy, the inverse of this guy. And C is just a scalar. So this thing is just a scalar. So inverse of a scalar is very simple. It's just 1 over this thing here. And so this whole thing will be just some matrix multiplication. So it will be much faster than computing this matrix, the inverse of this matrix again, by brute force. So, and as I mentioned, I like to write U and V as this FAC and FCA here. So it's kind of convenient for me because this reminds me that like basically this matrix, like FAC, have the number of rows is the same as the number of rows in A. Basically, okay, maybe I forgot to mention, but of course, like A and C here are square matrices, but this U and V or like FAC and FCA does not need to be square matrices. So something like I may have A is something like that. This is A here, and this can be my FAC of the size like that, and this is FCA, and my matrix C is also square matrix. And this matrix inversion formula is useful typically when this A has much larger size than this C here. So okay, as I mentioned, I write this U and V using this. Then it reminds me also like FCA will have number of rows the same as C and number of columns the same as A. And so then like when I write down this formula, I will remember like, okay, I don't think it's easy to remember this formula, but if you write it this way, it's actually easier to remember than writing U and V. Now you see that like I have this thing here, C inverse minus FCA. I have A is going to attach to A again, and A will attach to FAC instead of FCA. And then like this C thing here, this whole thing you can think of now is related to C. Should first go to C and then go to A, so it should multiply by FCA instead of FAC, something like that. So it helped me to remind it a little bit better. Okay, I will quickly go through the proof, and there's a number of proof for the matrix inversion formula. Of course, the most straightforward one would be simply this thing multiplied by this thing. You can show it this way, but I think a much more intuitive proof, but it won't be the shortest proof, but it's pretty much easy to derive and remember, is just consider the matrix A, FAC, FCAC here, just as what I did here. So I'm considering this matrix just composed of this A, FACC, and FCA matrices here. Just like putting puzzle together to form this bigger matrix here, and then like consider the inverse of this this big matrix here. So I can compute the inverse using the standard what I say, like elimination, Gaussian elimination technique. So for example, like I can write this as attached with an identity matrix here, and then what I can do is I do some kind of row operation. Each time I do row operation, I will basically multiply by a simple matrix on the, let's see, on the right hand side basically. So then okay, maybe let me elaborate a little bit. So when I go from this to this here, what I essentially is doing is basically multiply this matrix, multiply the original matrix by A inverse I, something like that, right? If I multiply A inverse I by this long fat matrix here, I'll get this. And so what happens if I can multiply a bunch of matrices, simple matrices, and that will equal to a whole thing eventually, to get this original matrix A, FAC, FCA, CII into something like I something. Then of course this something here multiplied by this guy is equal to identity matrix. Therefore this something here is actually just the inverse of AF AC FCA, see, the inverse of this guy. And of course this inverse of this guy multiplied by this identity matrix on this side will appear here. So therefore I will get the inverse here. So after a number of row operation, what I get is actually will have a form I and have the inverse of AF AC FCA C here. So okay, this is just some background information. I assume actually you know that, but maybe it's just a reminder if you don't kind of like recall it immediately. So now I just do this row operation. Basically, I have take A inverse here, multiply by A inverse for the first row here. Remember, like I can do that because FAC here have the number of row as A. So therefore, like if I have, actually be careful that I cannot multiply A inverse to, for example, FCA here. So that's why I find it more convenient to define like FAC and FCA instead of U and V. So okay, continue my operation here. I have this guy here. I can subtract this row. I should say subtract this row by this row multiplied by FAC. So FCA. Then the first component here for the second row here will be equal to 0, and then the second one here will be equal to this guy, and then so on, these terms here. And again, I can take the inverse of this thing. Basically, it's like this multiplied by IC minus FCA A inverse FAC inverse here. So if we multiply by this guy to this whole matrix here, I got this. And then again, I will subtract this, multiply this row by this A inverse FAC, and subtract this first row by that multiple, and then I will get this. The first part of this matrix is now identity. Therefore, this guy, as what we want, is actually equal to, although it's a little bit ugly, is A FAC FCA C inverse. So what is interesting here is that we kind of expect this guy is symmetric, right? Because this have a symmetric form here. I mean, it's symmetric in the sense that AC looks like symmetric, have some certain symmetry. But what we got here is that it has not a symmetric form here. So therefore, we can guess that probably there is another form of this guy will have this component, like will have this term similar to this component. What it means is I probably will have this first term here, or the upper left element here is something like A minus something blah 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 inverse, a term like this. And indeed it can be shown this way, because we can, instead of trying to first multiply this long matrix by A inverse I, we can multiply this long matrix by, I should write this multiplied by this guy by IC inverse. If I do this first, I have this guy, and basically do the same thing again, blah blah blah. Eventually I will have this term here, and this guy of course again is just AFACFCAC inverse. Therefore this guy is equal to this guy. So we just compare the term, the first term here, we'll have this A minus FACC inverse FCA inverse is equal to this guy here. And that's basically a quick proof of the matrix inversion for